Alright, let's discuss the difference in the use of large bulky bases versus smaller, more streamlined bases, and how we can use the transition state of the reaction to support the outcome. And so we've learned in class that the streamlined bases will give us the Zaitsev product, which is the more substituted alkene. So if I can draw the alkenes up here that we'd expect, I want to use a different color here. So this alkene will result from loss of HB, and this alkene will result from loss of HA. Okay, and we know that this one is the major product because that's what we learned, that the streamlined base, the smaller base, gives us the Zaitsev product. But really, the question is exactly why does that happen? So let's look at the transition state required for each of these reactions. Let's look at the loss of HA first. Remember that drawing a transition state essentially uses dashed lines to indicate any bonds that are breaking or forming. And so I can redraw my molecule starting material like that because I know that I'm breaking the CCl bond, I'm breaking the CHA bond, and I'm forming a new double bond between those two carbons. I'm also going to form a bond between HA and my base. And of course I have a delta minus on the base and a delta minus on the chlorine. So here's my transition state for loss of HA. And if we look at this, this sort of resembles the alkene. The forming alkene is right here, is more stable with more substituents, just like the actual alkene will be once we form it. So this alkene that's in the process of being formed has two substituents, just like the actual product will. And so that puts this one as the more stable transition state. And we'll look at how that compares on a chart in a second. Let me draw the transition state for loss of HB. I'm going to put that over here. And again, I need dashed lines for every bond that's being broken and that's being formed. Delta minus on the oxygen from the base, delta minus on the leaving group that's leaving, and then I put brackets around this and the double dagger. And if we look at the alkene that's forming here, this would be called a mono-substituted alkene. And that's going to be less stable than the potential di-substituted alkene. So this one is a less stable transition state. And of course, when we're referring to stability, we can draw a energy versus reaction coordinate diagram. We're starting from the same starting material, and I'm going to draw a low transition state and a high transition state. And so this is the EA for loss of HA. And I'll use a different color to show you the EA for the loss of HB. And so we can see that the energy level of these two transition states is different. And so the minus HA will form faster with this less hindered base. Yeah, so we can also look at the sterics here, and this is pretty small. There's one thing here, it's got some hydrogens on it, but really because we're using a smallish base, there's not a lot of steric interaction. So we can point that out here. That will be important in the next example. All right, so we can look at the transition state. We have a more sterically congested transition state for loss of HA, but we have a smaller base, so that's not too much of a problem. And we're making the more stable alkene. And so we get a more stable transition state, this one over here, the lower one, and that means that our major product will form more quickly. It's also more stable thermodynamically because our product has more substituents on the alkene than the loss of HP product. Let's look at the same alkyl halide, but with a larger base now. So this is a larger base. We're going to draw the same two products, of course, so I'll keep these blue ones up there. We're going to draw essentially the same two transition states as well. So let me see if I can reproduce those quickly. I'll use red again. So here's the loss of HB. The only difference is now I'm putting in a larger base. Delta minuses, got our transition state and our double dagger. And then I'll draw loss of HA. And again, our transition state with the double dagger. And so now the problem is here, we have some steric interactions. And I'm going to use a green to highlight that. We'll call that a strong. Strong is probably a better word here. Strong steric interactions. And that leads to a higher energy transition state. So it's destabilized. And over here, less steric interaction because our base is on the outside of the molecule. HB is much more accessible. And so now we know, of course, that this is going to be the major product. And we can look at an energy level diagram again, this time using the larger, bulkier base. And we're going to get two pathways again. I'll try to use two different colors in this case as well. And this is minus HB in this case. We have a lower energy transition state, but we also have a higher energy product, of course, because the Hofmann product, the less substituted alkene, is higher in energy. So we're not making the thermodynamic product here, we're just making the kinetic product because the transition state in this case is better. That's going to be this one, this loss of HB transition state. And then, of course, the other HA that's evident from this, the other EA is loss of HA. And that's going to be a higher energy transition state. And that's because of sterics. Right, and that's right here. We have strong steric interactions. Even though ultimately we form the more stable alkene, we're not going to form it as fast. And so the major product using larger bases is going to be the alkene that results from the more easily accessible hydrogen being removed. And typically that's on the outside of the molecule, and that gives us less substituted alkene. So here we can look at the sterics and the stability of these transition states to get an idea of which product forms the fastest.